Given bloom windows for each flower and arrival times for each person. Each flower is in full bloom from its start time through its end time, inclusive. For each person, count how many flowers are in bloom at their arrival time. Return those counts in the same order as the people array. Example 1, flowers 1 6, 3 7, 9 12, and 4 13, people arrive at times 2, 3, 7, and 11. Person at time 2, only the bloom from 1 to 6 is active. 1 flower in bloom. Person at time 3, blooms 1 6 and 3 7 are both active. 2 flowers in bloom. Person at time 7, blooms 3 7 and 4 13 are active. 2 flowers. Person at time 11, blooms 4 13 and 9 12 are active. 2 flowers. The output array is 1, 2, 2, 2. Example 2, blooms 1 10 and 3 3. A person at time 3 sees both blooms, so the count is 2. The next person also arrives at 3, still 2. A person at time 2 sees only bloom 1 10, so the count is 1. Output 2, 2, 1. If a single person arrives on day 3, finding how many flowers are blooming is simple. We look at every flower interval and see if day 3 falls between its start and end days. But if we have tens of thousands of people arriving at different times, scanning every single flower interval for every single person will completely freeze our system. We need a way to answer a person's question instantly without scanning intervals. Let's break down the lifetime of a flower. A flower is in full bloom if it has already started blooming, and has not yet finished. This means the number of flowers in bloom at any given moment is just a simple subtraction, the total number of flowers that have ever started blooming up to that day, minus the total number of flowers that completely finished before that day. This insight allows us to make a massive simplification. We can completely destroy the intervals. We don't care which specific flower belongs to which timeline anymore. Instead, we can separate the start events and the end events into 2 entirely independent lists. Once we have separate lists, we sort both of them in ascending order. Why? Because sorting organizes time. If we want to know how many events happened before a certain day, having our lists arranged chronologically makes finding that count incredibly fast. Now let's test our formula for a person arriving on day 3. First, we look at our sorted starts list. Using binary search, we can instantly find the boundary of elements less than or equal to 3. The search highlights all 3 elements, telling us that 3 flowers have successfully started blooming by day 3. Next, we look at our sorted ends list. We want to find how many flowers completely finished before day 3. We use binary search to look for elements strictly less than 3. The search drops right at the beginning, showing that 0 flowers have finished yet. Finally, we plug these 2 results into our formula. 3 started, minus 0 finished, leaves us with exactly 3 flowers in full bloom. By using sorting and binary search, we can answer this question for any person in logarithmic time, completely bypassing the brute force trap. We begin by decomposing our flower intervals. We loop through the input array and extract every start day into a dedicated starts list, and every end day into an independent ends list. We completely decouple the timelines. Next, we sort both lists independently in ascending order. This chronological layout is crucial. It transforms our random event days into structured timelines that we can query with binary search. We initialize a results array, matching the exact size of our incoming people list. This ensures we have a dedicated slot to store the final blooming count for every single visitor. Now we loop through each person's arrival time. For a person arriving on day 3, we execute our first binary search over the starts timeline. We look for the first position greater than 3, which lands at index 3. This tells us exactly 3 flowers have already started blooming. Next, we run our second binary search over the ends timeline. Since a flower ending on day 3 is still fully in bloom on day 3, we look for elements strictly less than 3. Our search stops cleanly at index 0, proving that 0 flowers have finished blooming before this day. We perform our master subtraction right inside the loop. By taking the 3 flowers that started, and subtracting the 0 flowers that ended, we deduce that exactly 3 flowers are currently in bloom. We save this count to our results array. Once all arrival times are successfully computed in logarithmic time per person, our loop finishes. We return our fully populated array, completing a highly efficient, timeline-shattering solution. N is the number of flowers, and M is the number of people. Time is O of n log n plus m log n. We sort the start and end lists once, then each arrival runs 2 binary searches on those sorted timelines. Space is O of n for the 2 sorted event lists. Our main routine counts blooms for each person arrival. Make an empty list for start days. Make an empty list for end days. Walk every flower interval. Push its start day onto starts. Push its end day onto ends. Sort the start days in ascending order. Sort the end days in ascending order. Allocate 1 answer slot for every person. Loop over each person index. Read that person's arrival time. Upper bound is a binary search that counts how many starts are less than or equal to that time. Store that count as started. Lower bound is a binary search that counts how many ends are strictly less than that time. Store that count as ended. Bloom count is started minus ended, store it in the answer. Return the filled answer array.